Welcome to today's paper reading. Today's paper is titled PEDAL, Enhancing Greedy Decoding with Large Language Models Using Diverse Exemplars. This paper was published on the AR14 preprint by Sumanth Prabhu from Parsamo AI. Self-ensembling techniques, such as self-consistency, have shown significant improvements in text generation with large language models, LLMs. However, these techniques rely on an accurate answer extraction process and incur higher inference costs compared to greedy decoding. Recent research indicates that LLMs can reliably aggregate free-form text outputs. Additionally, the use of diverse exemplars and prompts has been shown to enhance the diversity of LLM outputs. Building on these findings, this paper introduces PEDAL, a hybrid self-ensembling approach that combines diverse exemplar-based prompts with LLM-based aggregation to improve overall performance. Experiments on SVAMP and ARC datasets demonstrate that PEDAL achieves better accuracy than greedy decoding strategies while maintaining lower inference costs compared to self-consistency approaches. The introduction of this paper highlights the performance of large language models, LLMs, and natural language understanding tasks, showcasing their remarkable reasoning capabilities. However, these models still depend on carefully designed prompts for optimal performance. To enhance LLM reasoning, the authors discuss the self-consistency (SC) technique, which aggregates diverse reasoning paths to improve response accuracy. Despite its success, SC has limitations such as reliance on fixed answer sets and high inference costs. To address these issues, the paper introduces PEDAL, a hybrid self-ensembling approach that leverages diverse exemplars and greedy decoding to achieve better accuracy and lower inference costs compared to traditional methods. In the related work, researchers have applied large language models, LLMs, across various fields such as healthcare, finance, and law. However, no single LLM consistently outperforms others across all tasks, prompting the exploration of ensembling approaches. Self-ensembling strategies involve organizing model-generated thoughts into a tree structure for solution search, often relying on custom aggregation methods. Recent work has addressed this by using LLMs for majority consensus aggregation without fine-tuning. Prompt ensembling strategies have also gained attention, focusing on developing effective prompting techniques and multiple prompt ensembling to improve performance. Additionally, efforts have been made to reduce LLM inference costs through various techniques. Figure 1 provides a high-level overview of the PEDAL system, which is designed to enhance text generation using large language models, LLMs. The system operates by first generating multiple candidate responses through greedy decoding, using prompts constructed from diverse exemplars. These candidate responses are then aggregated using the same LLM to produce the final output. This approach aims to improve accuracy while reducing inference costs compared to traditional methods. In this methodology, the authors employ greedy decoding to generate candidate responses using multiple language model, LLM, prompts. These prompts are constructed by randomly sampling exemplars for in-context learning, ICL, with different seed settings, enhancing the reasoning capability of the language models. The final response is then aggregated using the USC method, which selects the most consistent response among multiple candidate responses through majority consensus. In this section, the author mentions the use of two publicly available datasets for conducting experiments. However, specific details about the datasets, the experimental setup, and the key findings are not provided in the text provided. To fully understand the experiments and their outcomes, one would need to refer to the complete section of the paper. In the SVAMP dataset, PEDAL demonstrates significant improvements over greedy decoding. With QuEN2, PEDAL achieves an average accuracy of 77.89%, which is 1.89% higher than greedy decoding's 76%. Similarly, with Llama 3, PEDAL's accuracy of 74.11% is 3.89% higher than greedy decoding's 70.22%. On the ARC dataset, PEDAL also shows improvements. With QuEN2, PEDAL's accuracy of 83.77% is marginally better than greedy decoding's 83.38%. With Llama 3, Petal's accuracy of 78.55% is 2.03% higher than Greedy Decoding's 76.52%. In terms of token efficiency, Petal processes fewer output tokens, making it more cost-efficient compared to USC, which uses significantly more output tokens. Table 1 provides the validation dataset sizes for SVAMP and ARC datasets used in the experiments. The SVAMP dataset includes 300 validation samples, while the ARC dataset includes 345 validation samples. Notably, the ARC dataset is restricted to the ARC challenge partition, which contains more difficult questions requiring reasoning. Table 2 presents a performance comparison of Greedy Decoding, USC, UDE, and Petal on the SVAMP dataset, measured by accuracy. The table shows that Petal consistently outperforms Greedy Decoding, with a notable improvement of 1.89% with Qwen2 and 3.89% with Llama 3. USC achieves the highest accuracy, particularly with Qwen2 at 80.33%. Petal also surpasses UD, which records an accuracy of 75.67%. The results highlight the effectiveness of Petal in enhancing accuracy over traditional methods. Table 3 presents a performance comparison between USC and Petal on the SVAMP dataset, focusing on the number of output tokens processed. For Qwen2, USC handles approximately 903 input tokens and 503 output tokens, while Petal processes 1,343 input tokens with only 192 output tokens. With Llama 3, USC averages 694 input tokens and 924 output tokens, whereas Petal manages 1,262 input tokens and 198 output tokens. This data highlights Petal's cost efficiency in terms of output tokens, making it a more economical choice. Table 4 presents the accuracy performance of different strategies on the ARC dataset. For Qwen2, Petal achieves an average accuracy of 83.77%, a slight improvement over Greedy Decoding's 83.38%. UD outperforms Petal with an accuracy of 84.06%, while USC achieves the highest accuracy of 84.35%. With Llama 3, Petal shows a 2.03% improvement over Greedy Decoding, achieving 78.55% accuracy compared to 76.52%. UD matches Greedy Decoding's accuracy of 76.52%, and surprisingly, USC performs the least among the strategies with an accuracy of 71.88%. The table highlights the best performing strategy for each model, emphasizing the performance metrics of the proposed approach. Table 5 highlights the efficiency of Petal compared to USC in processing output tokens for the ARC dataset. For Qwen2, USC processes approximately 668.71 output tokens, while Petal significantly reduces this to 99.47 output tokens. Similarly, with Llama 3, USC processes 928.1 output tokens, whereas Petal manages with only 196.83 output tokens. This demonstrates Petal's superior efficiency in terms of output token usage across different models. Table 6 illustrates the impact of varying the number of prompts on the performance of Qwen2, a model evaluated on both the SVAMP and ARC datasets. The table presents average scores across 3 different seed settings, along with the standard deviation, to provide a comprehensive view of the model's consistency and performance under different prompt conditions. This analysis helps in understanding how the number of prompts influences the model's accuracy and reliability in handling diverse datasets. In this paper, the authors explored the use of self-ensembling with large language models, LLMs, using diverse exemplars and LLM-based output aggregation. They found that this combination can outperform Greedy Decoding in terms of accuracy and offer better cost efficiency compared to methods based on sampling and consensus, SC. However, the experiments were limited to small datasets, allowing for benchmarking using exact match without the need for additional manual annotation. For future work, the authors plan to extend these ensembling strategies to a broader range of problem settings, particularly those involving free-form text generation, to further investigate the strengths and weaknesses of their proposed system. Thank you for watching.